Relativity Part 2, Something We Can Agree On. In Part 1, we looked at the unexpectedly weird consequences of postulate number 2. If light is always observed to be going the same speed, then the Martian will disagree with the space traveler about what time is and how long things are. The Martian will be aging more quickly, will be older than the space traveler, and will see the spaceship as shorter, as squished. All this just because the ship is moving. Dilated and contracted by gamma, the Lorentz contraction factor. And that's not all. Other quantities like mass, energy, and momentum also get stretched. We're gliding over these proofs. I hope you don't mind. Hey look, E equals mc squared. But that's not the point. The point is, can't we agree on anything? And yes we can, and that's what this video is about. First, however, a paradox. Consider an athlete and a farmer. Without relativity, at rest or at slow speeds, they both agree that this pole just barely fits into this barn. So what happens when we, quote, turn relativity on? Will the pole still fit? Yes, says the farmer. The barn is at rest and the athlete is running towards it. The pole is squished and easily fits. But not from the athlete's point of view. To her, the pole is at rest and the barn is moving towards it. Just like, when you're in a car, hey, that next street is coming up on your right, or the trees or the telephone poles are whistling past you. To the athlete, the pole is at rest and the barn is moving. So what? So, the barn is moving, it's squished. The pole does not fit in the barn. And that's the paradox. Does the pole fit or not? The answer, say it with me, 3, 2, 1, it's relative. And this time, it makes me happy, because there is something the farmer and the athlete can both agree on. And to find out what that is, let's bring in some numbers. Same basic problem with a twist here, only this time. At rest, the pole is 6 meters long, and the barn at rest is 3 meters long. So without relativity, no, it definitely does not fit in the barn. The athlete runs at about 67% of the speed of light, so work out the details with me, and the Lorentz contraction factor is 2. Which means that with relativity, the pole just barely fits in the barn as seen by the farmer. It was squished to half its rest length. And the pole definitely does not fit in the barn according to the athlete. So this is great. But what can they agree on? On these two events. The details make your head spin, but these are the two events that we are concerned with. So what does it mean to not fit anyway? It means that event 1, the front of the pole leaving the barn, happened before event 2, the back of the pole entering the barn. That's what it means to not fit. And yes, it makes your head spin, but these are the events we care about. Why do we care about them? Because we can graph them. What the farmer sees, the squished pole fitting in the barn, we can graph that on a space-time graph, which is not as complicated as it sounds. See the barn? It's moving straight upwards in time. See the pole? It moves at an angle. It's moving at a velocity. So what's so great about this graph? I'll give you two things, two events. The two events that we're concerned about. They're simultaneous here, but who cares? The farmer has a graph, so what? The athlete will have a completely different one. The squished barn moving to the left. The pole not fitting. Yeah, we can graph that too. Great, but different. You said you wanted something these two observers could agree on. It doesn't look like you found it. The same two events, but two totally different graphs. Here the front leaves before the back enters. No fitting. The same two events on two different graphs. What's the same about these two? Well, we've got something else. We've got numbers. Nothing too sophisticated here. D equals VT gives us good values for when the events happen. We already know where they happen, and here's something you may not know about. The space-time interval. What's that? I have no idea, but it's the answer. It's the thing we've been looking for. Again, we wanted something that the two observers would agree on, and we've found it. Work out the numbers for yourself. And it does make sense, after all, that we would be able to find something they could agree on. These are the same two events. So, everybody 2.5 cheers for the space-time interval. Just 2.5, though. It's weird. And wait a minute. Are you going to take a square root of that negative number? Yep. Turns out that these two events have that kind of space-time separation. Weird. But constant, more than constant, a super constant, an invariant, the same. It's the same for all observers. And it's so super that we'll have some fun with it. And you know what that means. derivatives, both with respect to time and distance, so you better use the function rule. And I have to admit that I'm not really in the mood for the gory details. I usually am, but not right now. But here's the takeaway. d tau dt equals c squared t over tau, which must be constant over there. d tau ds equals s over tau, which is also constant, a different constant. But now, back to the space-time formula, so we can rearrange it and do something unjustified and hand-wavy and illicit and almost immoral. I am deeply troubled by this next step. Not really, but if I was troubled by any step, it would be this one. Now I'm going to guess what d tau dt equals. I have no good reason for it. Just go with it or turn the video off in disgust. So, holding our noses there, d tau dt equals gamma times c, a constant. And without it, we'd be stuck. But with it, we're anything but, because of these two friends. Hey, we neglected to prove them earlier. Hey, this video really is very hand-wavy. I'm sorry about that, but it's time to do some algebra in the left-hand corner. And that's random. What good is that? Well, glance upward a little bit. Ct over tau. That term is getting ready to jump into our space-time equation. First, though, momentum, you need a talking to. Momentum. Are you ready? Math. 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 Notice something? More math. And glance down. Get tweaked. See that? Almost done. And I'd like to thank you again for letting me let d tau dt equal gamma times c. I hope you agree it was worth it, because space-time now is getting all beefed up and tweaked and multiplied and rearranged and added to our list of invariants. It's a short list, but hey, these are things that all the observers can agree on. First was space-time interval. Let's call the second relativistic energy, or the energy-momentum relation, or the relativistic dispersion relation. It contains a term for the particle's rest mass. That's E equals mc squared. Using the rest mass, that's the rest energy, E equals mc squared, and the kinetic energy, Pc, the kinetic energy. And this is an equation that everyone can agree on, even though we may disagree about so many things: time, distance, simultaneity, energy, momentum, all those things we can disagree on, but these things, these invariants, all observers will agree on, and that is why, after all, I like relativity, even though I don't like disagreement, because it's about a new, deeper agreement. What are things we agree? We agree that energy is conserved, mass, angular momentum, lepton number, all three also conserved. Measurement 1, do something. Measurement 2, you get the same value for energy, mass, angular momentum, and other stuff. Space-time and rest energy and rest mass, they are like that too, only more so. Measurement 1 and 2 are not just the same for different times, they're the same for entirely different frames of reference. We found a new bedrock of agreement. We found invariance. Something the farmer and the athlete, something the Martian and the space traveler, all four of them, something they can agree on.